Dear participants, let me greet you all and congratulate you on the start of the 5th Olympiad of the World Metropolises. My name is Ilya Golovnin, and I'm one of the authors of the experimental task. Now I'm within the walls of Moscow State University, in the nonlinear optics laboratory. Next to me is the optical harmonic generation setup used for teaching students. The scheme of this setup was described in the text materials sent to you earlier. In connection with the current situation in the world, we have to hold the Olympiad in a distant format. However, I hope you find the task interesting. So, in this video, you will be shown in several experiments, each of which will be asked either qualitative or quantitative. Write your answers on the answer sheet. For questions that require verbal explanation, use only English and formulas. Try to write neatly and clearly so that the jury will be pleased to check your work. Good luck, and let's get started. The first part of our work will be related to birefringence. We will study it using a crystal of Iceland spar. I have such a crystal. It's transparent enough to observe the necessary effects with it. Also, I have an object printed on a piece of paper, and I have a small protractor for measuring angles. Now I fix the object on the special holder. Then I place the protractor on top of the object, this way. After that, I can put the crystal on the protractor, and in this way it will be possible to rotate the crystal and observe what happens to the object. Now we can observe two images. The question number 1. Which of the images is formed by ordinary rays and which by extraordinary? Question number 2. In the figure, draw the direction of projection of the optical axis on the crystal onto the horizontal plane. Draw this line through the center of the circle of the protractor. Write down the angles that this line crosses on the protractor scale. It can be noted that the images given by such a crystal are at different depth. It's easy to understand which one is deeper because of stereoscopic vision when we look at objects with two eyes. But this also be understood by observing objects from different angles while moving the camera this way. Now we rotate the crystal a little, and then move the camera in different directions. The question number 3. What of images of the object is deeper, which is formed by ordinary rays or which is formed by extraordinary rays? If the observed object is formed not on paper like we use, but on a smartphone screen, then we can observe other interesting effects. Let's take a photo of our object. And then adjust the image on the smartphone screen so the object is about the same size. Then put the protractor our crystal, and now let's repeat our experiment on crystal rotation. Note, now the position of the crystal relative to the protractor scale has changed. The question number 4a. What property of the smartphone screen is associated with switching between images? The question number 4b. What characteristic of this property can you determine? The question number 4c. Is it possible to depict this characteristic in the figure? And if possible, draw it. So far we have used Iceland spark crystals with natural cut. In many cases, practical application require crystals cut along the optical axis or perpendicular to it. It's quite difficult to visually determine the direction of optical axis of such a crystal. Therefore, it can be done using the so-called conoscopic picture. Now we will use the following optical system to observe the conoscopic picture. The beam of the laser is directed by two mirrors to the focusing lens. Then the light is focused by the lens into a crystal and then passes through the analyzer. After that, the light falls on the screen on which we can observe a certain picture. This is a real setup on which we will observe a conoscopic picture. We will use a helium-9 laser as the light source. A laser beam is reflected by two mirrors and falls on the screen. We can see the laser beam. Now let's insert the focusing lens. After focusing, the beam expands. Next, we put the crystal holder so far without the crystal and the analyzer. If you rotate the analyzer around the axis of propagation of the laser beam, we will notice that the intensity drops to almost zero at certain position of the analyzer. In this case, the plane of polarization of the analyzer is horizontal. Question number 5. Why does illumination of the screen disappear at a certain angular position of the analyzer? If we insert our crystal between the lens and the analyzer so that its optical axis is perpendicular to laser beam direction, we can observe the following conoscopic picture. In this case, we need to slightly adjust the angle of the analyzer to observe the characteristic pattern. Now let's set the position of the analyzer polarization plane strictly horizontal. And if we insert the crystal so that the optical axis is directed along the laser beam, we will see a completely different conoscopic picture. You can see two characteristic patterns in this picture. The first is a dark cross and the second one is dark and light rings. Further questions will concern only this conoscopic picture. Look at the conoscopic picture. It's also on your answer sheet. The question number 6a. What is the polarization of the light before the analyzer on the vertical stripe of the dark cross? Draw the direction in the figure. Question 6b. What rays inside the crystal, ordinary or extraordinary, form the vertical dark stripe? Question 6c. What is the polarization of the light before the analyzer on the horizontal stripe of the dark cross? Draw the direction in the figure. Question 6d. What rays inside the crystal, ordinary or extraordinary, form the horizontal dark stripe? Question 6e. What is the polarization of light at most points in bright areas? Question 6f. In which direction is the polarization of the ordinary and extraordinary rays directed at a point that lies on the bisector of the angle between the dark stripes of the cross? Draw in the figure. If the crystal is illuminated not with a laser beam, but with a white flashlight, then the scheme for observation of the conoscopic picture changes. Light from a source passes through a polarizer. Then the light is focused by a lens into a crystal and then passes through the analyzer. The polarization planes of the analyzer and polarizer are perpendicular. Then the light falls on the screen on which we can observe a conoscopic picture. As a white light source, we will use a smartphone flashlight and a film polarizer placed after it. Let's replace the laser beam with a white flashlight with a polarizer. The conoscopic picture remains similar, but color separation in the rings can be seen. The color of a ring in the conoscopic picture is determined by the maximum intensity of light of a certain wavelength. The intensity distribution for different wavelengths is determined by the optical path difference of the ordinary and extraordinary rays for a certain point of the conoscopic picture. This kinescopic picture is generated as a superposition of the pictures formed by light of different wavelength. Question number 7a. Write down the formula linking the number of the ring measured from the center of the picture with the wavelengths of light corresponding to the color of the ring and with the optical path difference of the ordinary and extraordinary rays falling into a certain point of the ring. From B. Using formulas and inequalities, write a short explanation of why the red ring of some number is larger in diameter than the blue or green ring of the same number. When answering this question, disregard the phenomenon of dispersion. In the second part of our work, we will focus on optical harmonic generation. On a real experimental setup, we can see the process of second and third harmonics generation. The experimental setup is quite complex, so we will study its main components in sequence, first in the diagram. We will use a pulsed laser with a wavelength of about 1 micron. You can find the exact value of the wavelength in the description and in the answer sheet. We will call this radiation the first harmonic or fundamental harmonic. We don't always need maximum laser power. Therefore, to adjust the power in the laser beam, we will use a half-wave plate and a polarizer. We can rotate the half-wave plate around the axis of laser beam propagation and change the beam power after the polarizer. We will measure the power of laser beam using a special device called an optical power meter. In order to constantly monitor the power of the first harmonic, we will reflect a small part of our beam onto a photodetector 1 using a beam splitter plate. In order for the photodetector to work correctly without saturation, we will use attenuating neutral density filters. Now we see the real setup, which we studied according to the diagram. It's a laser. This is a half-wave plate that can be rotated. The polarizer is located here. Then there is a beam splitter plate which directs a small part of the radiation into the photodetector 1. This is a neutral density filters. And in the end of optical table there is a power meter. You may also notice other components on the optical table, but they don't bother us now, and we will discuss their purpose later. Now switch on the laser. The human eye cannot see infrared radiation with this wavelength, but you can check that the laser works with the help of a special visualizer or by burn on photographic paper. The signal corresponding to this power level is registered by photodetector number 1. Then the laser beam passes through the setup elements and enters the power meter. We can observe the signal level from photodetector 1 on the computer screen. As you remember, we use the half-wave plate and the polarizer to change the power level of the laser beam. We can change the angle of rotation of the half-wave plate. You can see that when the half-wave plate is rotated, the laser beam power changes from the maximum value to the minimum. The question number 8. At what angle you should rotate the half-wave plate to change the laser beam power from the maximum to the minimum value? The laser generates rather short light pulses of 10 nanosecond duration. We will assume that the shape of the laser pulses is rectangular. The repetition rate of light pulses is 2.5 Hz. With our power meter, we can measure the average laser power. The full scale of the power meter in this case is 10 milliwatts. Therefore, the average power of laser radiation which the device shows is 3 milliwatts. So now the average laser power is 3 milliwatts. The question number 9. What is the peak power of the laser beam? When the power of the laser beam changes, the readings of the power meter and the signal level from the photodetector change synchronously and proportionally to the power of the laser beam. Therefore, the readings of the power meter and photodetector can be matched to each other at different laser radiation powers. This procedure is called photodetector calibration. This must be done so that later in the measurement process it would be possible to simultaneously read the signal levels from several photodetectors. In our case, we will not focus on calibration, but you need to know that all photodetectors used in our setup have been calibrated appropriately for each wavelength. Next, we will consider the process of the second harmonic generation using the general scheme first. We already know the first part of the setup. The first harmonic enters a nonlinear crystal, which is fixed on a rotation stage. This stage allows the nonlinear crystal to be rotated in the horizontal plane to find the angular phase matching. As you remember, when the phase matching conditions are met, we will obtain the maximum conversion efficiency to the second harmonic. In this case, the conversion to the second harmonic occurs using the first type of synchronism. That is, the frequencies of two ordinary waves are added and an extraordinary wave is obtained at doubled frequency. But not all the first harmonic is converted into the second, but only a part. Therefore, both second and first harmonic waves are emitted from the nonlinear crystal. In order to study the characteristics of only the second harmonic, we will place a special filter which only passes the radiation at the second harmonic frequency and absorbs the first harmonic. After that, a beam splitter plate is located in the setup, which reflects a small part of the second harmonic radiation into the photodetector 2. In front of the photodetector 2, as well as in front of the photodetector 1, attenuating neutral filters are placed. This is necessary for correct operation of the photodetector. And then the second harmonic enters the power meter. The calibration process for the second photodetector is the same as for the first one. Dependence of the second harmonic power on the crystal rotation angle, and the dependence of the second harmonic power on the first harmonic power. Checking how the laser works. Then turn off the laser. Now we place a nonlinear crystal for generating the second harmonic on the rotation stage. This is a KDP crystal of 4 centimeters long. And then place the filter which passes only the second harmonic. And observe the second harmonic generation. Now we need to adjust the angular synchronism to get the second harmonic maximum. We tune the rotation stage horizontally. It can be seen that at a certain angle the maximum of second harmonic is reached. This means that the phase matching condition is satisfied. The question number 10a. What is the second harmonic wavelength if the first harmonic wavelength is 1064 nanometers? The question number 10b. In what plane does the optical axis of the crystal lie? The question number 10c. In what plane does the first harmonic polarization lie? In the figure indicate the direction. The question number 10d. In what plane does the second harmonic polarization lie? In the figure indicate the direction. Now we will look at the process of cascading third harmonic generation. We will generate the third harmonic on a nonlinear crystal with quadratic nonlinearity as a sum of the first and second harmonics. Let's look at the scheme first. From the scheme for studying the second harmonic, we will remove the filter that absorbs the first harmonic and place this filter in front of photodetector 2 so that the radiation of the first harmonic doesn't get there. Next, we place a nonlinear crystal to generate the sum frequency. This crystal is also mounted on the rotation stage. This allows us to find the phase matching condition, but this rotation stage changes the angle of the nonlinear crystal in the vertical plane. In this case, conversion to the third harmonic occurs using the second type of synchronism. The frequencies of the ordinary and extraordinary waves are added and an extraordinary wave is obtained at the tripled frequency. But not all the energy of the first and second harmonic is converted to the third harmonic. Therefore, waves of all three frequencies will be output from the crystal. To pass only the third harmonic, we put a filter that absorbs the first and second harmonic. Then we place a beam splitter plate which reflects a small part of the radiation into the photodetector 3, in front of which we also place neutral density filters. And then the third harmonic radiation enters the power meter. The calibration process for the third photodetector is similar to the process for the first and second photodetectors. This scheme allows us to measure the dependence of the third harmonic power on the power of the first or second harmonic. We have the filter that only passes the second harmonic. We place it in front of the photodetector 2. Now both waves, the first and the second harmonics, leave the nonlinear crystal and propagate further. We put another nonlinear crystal to generate the third harmonic. Then we place a filter that only passes the third harmonic. After the filter, we have beam splitter plate that reflects a small part of radiation into the photodetector 3. Then switch on the laser. And then adjust the phase matching angle for the crystal which generates the third harmonic. Remember that the angle of rotation of this crystal lies in the vertical plane. Now you can see the process of angle adjusting to reach the maximum of the third harmonic. The question number 11a. What is the wavelength of the third harmonic radiation? The question number 11b. In what plane does the optical axis of this crystal lie? The question number 11c. In what plane does the polarization of the third harmonic radiation lie? In the figure indicates the direction. The question number 11d. What wave, ordinary or extraordinary, is the radiation of the first harmonic for this crystal? The question number 11e. What wave, ordinary or extraordinary, is the second harmonic radiation for this crystal? Next, we will investigate how the second harmonic is generated in 3 KDP crystals of different length. We have crystals of 0.5, 2 and 4 centimeters long. These nonlinear crystals are hygroscopic and can deteriorate from atmospheric humidity. Therefore, they are closed in special boxes with transparent entrance and exit windows. For each of these nonlinear crystals, we will measure the dependence of the second harmonic power on the first harmonic power, and then we will measure the dependence of the second harmonic power on the crystal rotation angle. Now we arrange our setup to investigate the second harmonic generation in 4 cm crystal of KDP. I will change the power of the first harmonic by half wave plate rotation and measure the dependence of the second harmonic power on the first harmonic power. To block some parasitic light, we will use additional screens for our photodetectors. And we will average the power of radiation over 10 pulses. Let's start. We will repeat the same measurements of the second harmonic radiation power versus the first harmonic radiation power for the remaining two crystals. We've measured experimentally the dependence of the second harmonic power on the first harmonic power for 3 kdb crystals of different lengths, 0.5, 2 and 4 centimeters long. Your answer sheet have tables of all measurements. Look at the dependence of the second harmonic power on the first harmonic power for each of the crystal. The question number 12a. What is the maximum conversion efficiency to the second harmonic from the first for each of the crystals? 0.5, 2 and 4 centimeters. Write down the result as a percentage. The question number 12b. Is it possible to apply the fixed field approximation for each of the kdb crystals of different lengths? 0.5, 2 and 4 centimeters. The question number 12c. To what function of the first harmonic power should be proportional the second harmonic power theoretically? The question number 12d. The dependence of the second harmonic power on the first harmonic power can be expressed as follows. From the experimental data, calculate the power b to which you need to raise the power of the first harmonic to get a result proportional to the power of the second harmonic. Also calculate the proportionality factor A. The calculation must be done for all 3 kdb crystals of different length. Record the results on the answer sheet. Now let's measure the angular dependence of the second harmonic power. The rotation stage is automated, so we start and wait for result. We will repeat the same measurements of the second harmonic radiation power versus the crystal rotation angle for the remaining two crystals. Before we ask the next question, let me explain some experimental facts that relate to the angular dependence. For a 0.5 centimeters long KDP crystal, the angular width of phase matching is 3.75 milliradians. We can observe the characteristic form of this dependence, which is very similar to the function sine u divided by u squared. The next crystal is KDP 2 centimeters long. Its angular width of phase matching is 1.03 milliradians, and the characteristic form of the angular dependence is now worse. And for KDP crystal of 4 centimeters long, the angular width of phase matching is 0.62 milliradians. For this crystal, the characteristic form of the angular dependence is not observed. If we plot all three graphs together, we can see how the characteristic form of the angular dependence and the angular width of phase matching change with a change in length of the crystal. The shortest crystal has the largest angular width. This can be explained by the fact that the first harmonic radiation incident on the crystal is not a plane wave and has some angular divergence. For the shortest crystal, for which the angular phase matching width is large, the divergence angle of the first harmonic beam can be considered small. The radiation of the first harmonic can be considered an almost plane wave. Therefore, a characteristic form of the angular dependence for the second harmonic appears. For the remaining crystals, the same angular beam divergence can no longer be considered small. In order of magnitude, it's comparable to the angular phase matching with the KDP crystals of 2 and 4 centimeters long. Therefore, the characteristic form of the angular dependence is blurred for these crystals, and the measured angular phase matching width is greater than that calculated theoretically. The question number 13. Assuming that for the shortest KDP crystal, the incident wave of the first harmonic is a plane wave, calculate what width of angular phase matching should be obtained for KDP crystals of 2 and 4 centimeters long. As follows from the theoretical description of the second harmonic generation process. The second harmonic power should be proportional to the square of the crystal length. The question number 14a. Using the experimental data on the dependence of the second harmonic power on the first harmonic power for all crystals, plot the dependence of the second harmonic power on the crystal length for the same maximum possible power of the first harmonic. The question number 14b. Can this dependence of the second harmonic power on the crystal length be expressed in terms of a power function? If possible, indicate the degree. The question number 14c. Briefly describe the reason why the experimental dependence of the second harmonic power on the crystal length differs from the theoretical one. We arrange our setup for third harmonic generation. We have KDP crystal for second harmonic generation, for third harmonic generation, filter, and 3 photodetectors. But before we start, we remove the nonlinear crystal for third harmonic and observe the readings of photodetector 3. If we block the laser beam before the photodetector 3, we can see that readings change. Unblock, block. Probably this fact helps you to answer some questions. Now we will measure the dependence of the third harmonic power on the first harmonic power. And now we will measure the dependence of the third harmonic power on the second harmonic power. Experimental data for the dependence of the power of the third harmonic on the power of the first and second harmonics is in your answer sheet. The question number 15a. What function of the power of the first harmonic should be proportional to the power of the third harmonic theoretically? The question number 15b. What function of the second harmonic power should be proportional to the third harmonic power theoretically? The question number 15c. The dependence of the third harmonic power on the first harmonic power or the second harmonic power can be expressed as follows. From the experimental data, calculate the power b to which you need to raise the power of the first harmonic to get a result proportional to the power of the third harmonic. Also calculate the proportionality factor A. The question number 15D. From the experimental data, calculate the power b to which you need to raise the power of the second harmonic to get a result proportional to the power of the third harmonic. Also calculate the proportionality factor A. The question number 15E. Briefly describe the reason why the experimental dependencies of the third harmonic power on the first and second harmonics power do not coincide with the theoretical ones. That's all we wanted to show you in our video. Hope you find it interesting. I wish you all the best. Goodbye.